Okay, welcome to Let's Get to the Marks. This is question 5 of the 2023 Chemistry A-level paper for AQA, and it's on the Born Haber cycle. So this question is about metal chlorides. Table 2 shows some enthalpy data. We got the enthalpy of hydration for calcium 2 plus ions and for chloride ions, and then we have the lattice enthalpy of formation for calcium ions. Calcium chloride. User data in table 2 to calculate the molar enthalpy change when you dissolve calcium chloride. Now, do you know what that's called? That's called the enthalpy of solution when you're going to dissolve something. So we're kind of looking at a Born Haber cycle. This whole question is about the Born Haber cycle, but for enthalpy of solution, you do very similar to your Hess's law, how you set that out. So we've been given the hydration of calcium 2 plus ions and the hydration of chloride ions. The hydration is when you convert them from gaseous state to their aqueous state. And we've been given the energy change for that. And I've circled those in blue here. Now we've also been given gaseous calcium and gaseous chloride coming together to make a lattice, solid calcium chloride, which is an ionic lattice. And that's minus 2237. That's the enthalpy of lattice formation. So we can now set this out and do a little calculation to work it out. So what the question's asking us is how much energy, or what is the enthalpy change when you take calcium chloride solid and we form it into, we dissolve it basically into calcium 2 plus aqueous and calcium and chloride ions aqueous. We've got 2 chloride ions, by the way. So that's what we're looking for. So now we've got to try and use this data. Well, we've got the enthalpy change of solution that we're trying to find out, which is basically the energy change when you dissolve an ionic compound. So what have we been given? Well, we've been given calcium gaseous to calcium aqueous, which is the hydration of calcium. We've been told that that's minus 1650. We've also been given chloride gaseous to chloride aqueous, and we've been told that's minus 364. I'm circling these here. So we can write these out here and we can put those numbers in. Now we know the arrows go up. You just follow the arrows as they are in the table. So you create the arrows like they are in the table once you've set out your equation at the top for dissolving calcium chloride. We have to remember there are 2 chloride ions, and the data in the table doesn't have a 2 in front of it. It's only per mole. It's for 1 chloride ion. So we need to times minus 364 by 2. So now we've set that data out, lovely jubbly. We'll circle that there. We're going to come over here. What do we do over here? Well, this is a bit unusual. We've been given the formation of calcium gaseous and chloride ions in the gaseous into the lattice. This is the lattice enthalpy of formation, and it's minus 2237, and I'm circling that here. This is minus 2237, so we write that in here. Now, what we can do with these numbers is we know, remember Hess's law, it doesn't matter which route you take, the overall energy change is the same. So if I want to find out that top route with the question mark, I just draw an arrow going round here. I've chosen a lovely purple color. We're going to draw an arrow going all the way around, and we're going to go in this direction, and the overall energy change will be the same. So let's just look at those arrows. Now, wherever my pink arrow or purple arrow goes against the other arrow, you reverse the symbol. And that's because this is actually going from the lattice formation energy. We're changing this into lattice dissociation enthalpy. So it's the opposite. So it's plus 2237. Because look at my arrows, they're going in opposite directions. Now my purple arrows go in the correct direction with the enthalpy of hydration. So we're just going to go 2237 minus 1650, or plus minus 1650, however you want to write it, plus minus 364 times 2. Smash that all in your calculator, and you're going to get your answer for 2 marks. And you should get an answer of 100 minus 141 kilojoules per mole. And there you go. And don't forget, it's best to pause the video with each question and have a go before unpausing and watching my walkthrough. Okay. You can find all of these exam papers and these questions on the AQA website. So good place to go. Physics and Maths Tutors, another fantastic site where you can find most of the materials I go through with these walkthroughs. All right. Let's move on to the next question. This is 5.2. Use your answer to question 0.0 0.5.1 to deduce how the temperature changes when calcium chloride dissolves in water. So what did we learn about that enthalpy of solution, which is the energy when we dissolve calcium chloride? What we learned is that it's minus 141 kilojoules per mole. What does the minus tell you? That tells you it's an exothermic reaction. That negative enthalpy change tells you it's exothermic. That means energy is released. So what's that going to do to the temperature? That's right, it's going to increase the temperature. The energy release will increase the temperature of the solution. So we'd expect a temperature rise. And there you go. That's your mark. Right, let's look at 5.3. Explain why the enthalpy of hydration of fluoride ions is more negative than the enthalpy of hydration of chloride ions. So if you hydrate, chloride ions were minus 364. So they're basically saying fluoride ions will give you a bigger number, like minus 500 or minus 400, but bigger than minus 364 when you hydrate gaseous fluoride ions to aqueous. Why is that? Well, think about the only difference you can think about. They're both in the same group, same electrons in the outer shell. So what's the difference? Chloride ions are a lot bigger. Fluoride ions are smaller. Okay, they have less electrons, less shells. And what that means is that the fluoride ions have a higher charge density. That negative charge is spread over a smaller area, making them more impactful. And what that means is that they have a stronger attraction to positive things. Now, what's positive on a water molecule? You got it. The hydrogen part of a water molecule is delta positive. Now, don't say the hydrogen atom is positive, because that would mean that water is an ionic compound. It's not. So water's a covalent molecule, but we know that the hydrogen is slightly positive. We use that delta positive sign. And what that means is that there's a stronger attraction between the fluoride and the positive, slightly positive hydrogen on a water molecule than there is between a chloride ion and the hydrogen on a water molecule. And there we go. So basically, the fluoride ions are more energetically stable. They form a more energetically stable bond with water, therefore releasing more energy. So they're more thermodynamically stable when they bond with water molecules. And that's why their enthalpy of hydration is more negative. Okay, coolio. So that's 5.3. I hope you like, share, subscribe, and all that business as we move on. So make sure you hit the like. It's a little bit of a pain in the butt, I know, hitting the like button, but it really helps out the algorithm reach other A-level students and people that might be looking for this material or that find it helpful. Obviously, if you don't find it helpful, don't hit the like. Anyway, yeah, just showing you here. Here's a fluoride ion bonding with a hydrogen ion on a water molecule, and of course there's a chloride ion badly drawn bonding to a hydrogen on a water molecule, and that's going to be a weaker attraction with the chloride ion than you'll get with the fluoride ion. And the reason is fluoride is smaller, so it has a higher charge density. Okay, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
5.4, figure 2 shows an incomplete Born Haber cycle for calcium chloride. So you got one of these. People find these really difficult, but Born Haber cycle, here we go. Right in the missing formulas. So you can see there's two blank lines, one right at the top and one in the middle there. Well, what we've got at the bottom there is the lattice formation enthalpy, and then we've got going up from that, we've got calcium solid plus chlorine gas. You can see here the first one, and as we move up, what we're going to do, we're going to turn those calcium solid into gaseous calcium. What do we call it when you turn an element from its natural form into its gaseous form? And that is going to be the enthalpy of atomization. So we're atomizing the calcium atoms. They're being atomized. Now, so you need to write that out. CAG in gaseous form plus Cl2 still in gaseous. Now, as you go up to the next stage, what have we done? We've ionized the calcium to 1+. So that's the first ionization energy of calcium. And then we've got the second ionization energy of calcium if we go to the level up, because it goes to calcium 2+ plus 2 electrons. But our chlorine gas is still a molecule. Have a look here. I'm going to circle it here. That is still a molecule. It's not been atomized yet. Yes, it's in gaseous form, but it's in molecular form, not atomized. So our next one at the top here, we need to write out an equation to show the atomization of chlorine. We need to keep the calcium as 2+. We're not reversing any of it. So we remove those 2 electrons. We're just changing the chlorine from a molecule to atoms, and you put 2Cl in gaseous. Now we haven't ionized the chlorine yet, so they're still atoms, they're not ions. That happens in the next stage as you go down on the right, and that's called the electron affinity of chlorine those chlorine atoms gain electrons to become chloride ions. All right, that'll get you your 2 lovely marks. Let's move on to the next question. Now I've kept the equations here because we're going to need it for this question. So I've kept all of those that we've just written in, and this is 5.5. Table 3 shows some enthalpy change data. We've been given a bit of data that matches every single one of these equations on the left here on the Born Haber cycle. We're just missing one, and they want us to calculate the second ionization energy of calcium. So if we go to the one just before the top, I'm going to circle it in blue here. This is the second ionization energy. That's the only one we don't have data for. So what we want to do is write the data in for all of the others and then try and work out that missing one, okay? So this is our second ionization energy of calcium. So what we're going to do, we're going to go to this data on the right-hand side and write all the numbers into the correct places. So I'm writing 193 here, and that's because that is the atomization of calcium. 590 there for the first ionization energy of calcium. We don't know the second IE. We know that 121 is for the atomization of chlorine, and minus 364 I've written in red for some reason. That is the electron affinity of chlorine. And remember, it's per mole, so you have to take account of wherever they put a big 2 or a coefficient on the equation. You're going to need to multiply in those situations, wherever there's a coefficient. And then we have minus 795 here. This is for the lattice enthalpy of formation of calcium chloride. Sorry, the enthalpy of formation of calcium chloride, and minus 2237 is for the enthalpy of lattice formation of calcium chloride, and that's on the right. Now, what we're going to do here, what you need to appreciate is that we can set this out as minus 795, the arrow going down, is equal to everything else in the opposite route. So the enthalpy of formation of calcium chloride is equal to, if you then follow up with your finger and go all the way around the other side, it's equal to all of that. So I've drawn an orange arrow here, and this shows that that minus 795 is equal to everything along that orange arrow. So we just got to write it all out. Minus 795 equals 193 plus 590 plus second ionization energy plus 121 times 2. Now, why am I timesing 121 by 2? That's because there's a coefficient of 2 in front of the chlorine, and then plus minus 364 times 2. Why am I doing times 2? Because there's 2 chloride ions, and remember, it's per mole. I've circled that in red on the table, the data table. And so all we need to do, and minus 2237, all we need to do is now simplify to work out what the second ionization energy is. So I'm going to add together all the positives to make 783, 193 plus 590. I'm going to multiply minus 364 by 2 and 121 by 2. And then we're going to simplify that out each time. I like to do it step by step because I'm going to make mistakes. Some people just bash this all in their calculator, do it all in one go. So I've now got 1025 plus the second ionization energy plus minus 728 minus 2237. So I'm going to add those minuses together. I'm going to get minus 2965. Now all I want to do is take the 1025 and add it to the minus 2965, and we're going to find that minus 795 equals the second ionization energy minus 1940. So what do I do now? I just plus 1940 to each side. So I'm going to plus 1940 to each side, and that means we're going to get rid of the 1940 on the right hand side to just leave second ionization energy, and you're going to take 1940 and add it to minus 795, smash that in your calculator, and you're going to get your answer, which is going to be 1145 kilojoules per mole, and that is the second ionization energy of calcium. And we know the first ionization energy was plus 590. Were we expecting a positive answer? Yes. Look at the first ionization energy. It's positive. So you would start to think the second one must be positive too. So you can use a little bit of lateral thinking to check if your answer's right. Explain why the second ionization energy of calcium is greater. So why was it 1145 compared to 590? Why was it that much greater? Why is it harder to remove an electron the second time from calcium? Remember, it's in group 2. So the answer is that you're taking an electron that is away that is going to be slightly closer to the nucleus. Why is it closer to the nucleus? Because there's a greater positive charge on a calcium plus ion, so that electron is going to be drawn in slightly closer to the nucleus. So the second electron's closer to the nucleus, or you could say here you're removing an electron from a positive ion, which you weren't before, so which has an overall positive charge. So there's greater attraction between the electron and the nucleus. Coolio, and either of these two would get you a mark. Either of those two comments there. Right, let's move on. We're nearly done with this question. So we just got a disgusting 6-mark question, which I don't have a lot of space to fit in, but let's go for it. Table 4 shows the lattice enthalpy on a perfect ionic model and lattice enthalpies from the Born Haber cycles for 3 metal chlorides. So we've got calcium chloride, potassium chloride, silver chloride here on the left-hand side of the table. We then have their enthalpy of dissociation when you look at the perfect ionic model. Okay, so when you assume that they are spheres, that is what the perfect ionic model is. It assumes that they are complete spheres. On the Born Haber cycle is where you do the calculation, and we can see that we can compare the two. They're never exactly the same. Now, compare the 3 values based on the perfect ionic model. Compare the values based on the perfect ionic model to the values from a Born Haber cycle for each compound. So the first thing we need to do, check out that keyword compare. Compare the 3 values on the perfect ionic model. So do that first. Which is the highest? What's a basic description? Right, calcium chloride has the largest perfect ionic model, or the largest lattice enthalpy when we consider the perfect ionic model. In fact, it's much larger than potassium chloride and silver chloride, which are quite similar. So I might want to say calcium chloride as the largest, potassium chloride and silver chloride are quite similar, their values. Why is this? What do you know about calcium ions compared to potassium and silver ions? Well, calcium ions have a +2 charge. Therefore, we're assuming that the ionic bond is stronger between a calcium ion and a negative chloride ion because, of course, there'll be a stronger electrostatic force of attraction between the calcium ion and the chloride ion. So we can assume that calcium chloride has stronger ionic bonds than the other 2 metal chlorides. And why is that? Potassium and silver are both K plus and Ag plus. So we would assume there that they have weaker ionic bonds, and that would get you all the marks for talking about comparing the perfect ionic model values. So you're just looking at that set of values separately on the left hand side for this first part of the question, and you're explaining why the calcium chloride has a bigger number than the other 2. Now we need to consider the perfect ionic model to the values from the Born Haber cycle. So now we need to look individually going across in a row. Calcium chloride go 223, whatever it is, 2223 to 2237. So what can we say about calcium chloride's perfect ionic model enthalpy to its Born Haber cycle lattice enthalpy of dissociation? That's what we have to think about for the next part of the question.
You're still here? It's over.